On September 6, 2017, the GOES-16 satellite recorded an X9.3 solar flare, the strongest in over a decade. 12 minutes later, high-frequency radio blackouts hit the sunlit side of Earth. Airline pilots over the Atlantic lost communication with ground control. This is what it looks like inside NOAA's Space Weather Prediction Center during an active watch. And in the next few minutes, you'll see exactly how forecasters spot a storm on the sun before it becomes a crisis on the ground. Here is the single most important thing to understand. Space weather forecasting is not astrology with better graphics. It's physics applied in real time to a target 93 million miles away that can shift the outcome in hours. The building itself sits in Boulder, Colorado, unremarkable from the outside. Inside, banks of monitors track the sun in wavelengths your eyes could never see. Extreme ultraviolet, X-ray, magnetograms mapping the sun's tangled magnetic field like a weather map of an alien planet. The sun has weather, not metaphorically, literally. Wind, storms, eruptions, and a magnetic field that twists, snaps, and releases energy equivalent to billions of hydrogen bombs in a matter of minutes. Consider the timeline of an actual watch. It starts small. A sunspot group rotates into view, dark and complex. Its magnetic polarity, tangled in a configuration forecasters call beta gamma delta. That's not jargon for its own sake. It's shorthand for instability. The more twisted the field, the more likely it is to snap. And when it snaps, it releases a flare. The flare itself travels at the speed of light. 8 minutes, and it's here. X-rays and extreme ultraviolet radiation slam into Earth's upper atmosphere, ionizing it, and radio blackouts follow almost instantly. No warning possible. None. By the time you detect the flare, its effects have already arrived. That is why the second wave matters more. Often, but not always, a flare is accompanied by a coronal mass ejection, a CME. This is the part people get wrong constantly, so let's be precise. A CME is not light, it's mass. Billions of tons of magnetized plasma, physically ejected from the sun's corona, traveling anywhere from 300 to over 3,000 kilometers per second. That's the payload that actually threatens power grids. And unlike the flare, it takes time to arrive, anywhere from 15 hours to 3 or 4 days. That gap is everything. It's the difference between a surprise and a warning. Here is the single most important thing to understand about how forecasters use that gap. Once a CME is confirmed, usually via coronagraph imagery from spacecraft like SOHO or the newer GOES coronagraph, analysts model its trajectory. Is it Earth-directed? What's its estimated speed? What's the orientation of its internal magnetic field? Because that orientation determines almost everything about the impact. That last variable is the cruel one. If the CME's magnetic field points north, aligned with Earth's own field, the two fields mostly deflect each other. Minimal impact. But if it points south, opposite to Earth's field, it can reconnect with our planet's magnetosphere and pour energy directly into it. And you cannot know which one it is until the CME's leading edge actually reaches a spacecraft called DSCOVA, parked roughly 1 million miles upstream from Earth. That gives about 15 to 60 minutes of real warning before impact. 15 to 60 minutes for something that can knock out transformers serving millions of people. That is why the room goes quiet during a strong watch. Not chaotic, quiet. Everyone is watching the same number, BZ, the north-south component of the incoming field. Negative BZ, sustained, is the number that changes everything. Connect that back to March 1989, Quebec. A geomagnetic storm, driven by a CME with exactly this kind of unfavorable orientation, induced ground currents that tripped Hydro-Quebec's power grid in 90 seconds. 90 seconds. 6 million people lost power for 9 hours in the dead of winter. Transformers as far away as New Jersey were damaged. That event is the reference point every forecaster in that building carries with them because it proved something uncomfortable. A storm from the sun can black out a modern industrial grid faster than a human operator can respond. Now, bring that back to the scale of what's actually possible. The 1989 storm was significant, but it was not the worst-case scenario. That distinction belongs to September 1859, the Carrington event. Telegraph systems worldwide failed, some operators receiving electric shocks, some equipment sparking and catching fire, even after being disconnected from power. If a storm of that magnitude hit today's infrastructure, models suggest damage to hundreds of large transformers, and outages lasting not hours, but months, in some regions, because those transformers are custom-built, expensive, and take a year or more to replace. That is the scenario the Space Weather Prediction Center exists to prevent, or at least soften. And that brings us to the conspiracy angle, because it's out there, and it deserves a direct answer. No, NOAA is not hiding an incoming apocalyptic storm. No, the government is not suppressing solar data to control panic. The truth is less cinematic, and more unsettling in its own way. This data is public. Anyone can watch the same X-ray flux charts, the same coronagraph images, the same DSCO-VR readings that professional forecasters use. The real story isn't concealment. It's that the warning window is so short and the infrastructure so vulnerable that even total transparency doesn't guarantee protection. That's the uncomfortable version, not a cover-up. A physics problem we haven't fully solved. Let's talk about scale for a moment, because it's easy to lose in the numbers. The Sun is the dominant object in this solar system by an almost incomprehensible margin. It contains over 99% of the mass. A single X-class flare can release energy equivalent to millions of hydrogen bombs, and it does this routinely, on a star that looks, from your backyard, like a calm yellow disk. You live your entire life under the direct influence of an object capable of violence on a scale that has no real analog in ordinary human experience. Most days, it doesn't matter. Some days, it does. That's the quiet dread underneath all of this. Not that a megastorm is imminent. It's that our entire electrified civilization, your home, your hospital, your bank, your phone network, is built on the assumption of a stable magnetic environment that the Sun has never actually promised us. So what does the Space Weather Prediction Center actually watch for, in practice, during an active period? Here's the checklist forecasters run through, and it's worth knowing because these are the same signals available to you. Number 1. X-ray flux from GOES satellites. This is measured on a scale from A to X, with X-class flares being the most powerful. And X9 is serious. Anything above X10 starts entering historically rare territory. Number 2. Coronagraph imagery, watching for halo CMEs, meaning the ejection appears to expand in a ring around the Sun's disk, a visual signature that it's heading directly at Earth. Number 3. The KP index, a global measure of geomagnetic disturbance, scaled 0 to 9. A KP of 5 marks a minor storm. A KP of 8 or 9 marks a severe to extreme event, the range where grid operators actually take protective action, like adjusting transformer loads. Number 4. Discovers real-time solar wind data, especially that BZ value. Negative and sustained is the one to watch. Number 5. NOAA's own storm scale alerts, G1 through G5, issued publicly, updated continuously, and available to anyone, including you, in real time. There's no hidden channel. The information is open. What's scarce isn't data. It's time. So bring this back to your own life for a second. If you live somewhere with an aging power grid, if your region has already had blackout stress from heat waves or storms, a strong geomagnetic event layers directly onto that vulnerability. Utilities do have mitigation plans now, partly because of 1989, partly because of newer standards adopted after research into Carrington-scale scenarios. But mitigation is not immunity. It buys time. It doesn't eliminate risk. Forward-looking, here's where this goes next. We are heading deeper into a period where more of daily life runs through space-based infrastructure, GPS timing, satellite communications, precision agriculture, aviation routing. Every one of those systems is exposed to the same solar variability that once just knocked out telegraph wires. As the current solar cycle continues, activity doesn't move in a straight line. It clusters. Active regions rotate in and out of view over roughly 27 days, and clusters of sunspots can persist for multiple rotations, meaning the same threatening magnetic complex can face Earth more than once. That is why the Space Weather Prediction Center never fully stands down. Even in quiet periods, someone is watching that magnetogram, waiting for the next beta-gamma-delta region to rotate into view. Watch the sunspot complexity. Watch the BZ. Those two signals, more than any headline, tell you whether an ordinary solar afternoon is about to become an extraordinary one. If this kind of invisible, planetary scale hazard is the kind of thing that keeps your attention, subscribe, because we track these systems: earthquakes, hurricanes, marine heat waves, and yes, solar storms, the way they actually behave, not the way headlines dramatize them. Like this video if you want more of this kind of breakdown. Share it with someone who still thinks space weather is science fiction, and we'll see you in the next one.